We have some great things to do today, such as learning how to solve differential equations. But before I start with that, I would like to see if anybody needs any help with the homework. I remind you that the first homework is due tonight. Any hint that I could give you, I'll be more than happy to help you with anything. So question 3, let me just say that the question 3 is very similar to what we did in class last time, and I'm going to explain it once more, but I would invite you to look at the recording. The idea for the last problem is as follows. So let me start working something similar. So you have, let's say, an equation like this: y prime is equal to 5y, and y of 0 is 1. So let's say you have something like this, and the question is approximate y of 1 in n steps. What does that mean? That means that you start at 0, you end at 1. Since you have n steps, it's as if you want to take the interval from 0 to 1 and divide it into n steps. So the step will be 1 over n, 2 over n, and so on, the points. So each step will be 1, right? And then you want to start by computing y prime of 0. Y prime of 0, which is the same thing that we denoted as y sub 0, is going to be simply 5 y, so 5 times 1, right? Which is 5. And then you will have y of 1 now. This is what I want you to understand. So pay attention to this, and then you will be fine. Y of 1 is going to be y of 0 plus y0 prime times the step. And how much is the step? 1 over n, we said, right? So this will be 1 plus 5 over n. Sorry, I'm just looking. Right. And then y1 prime will be 5y1, which is 5 uh, 5 times 1 plus 5 over n, right? And now ask yourselves about y2. Let's take one more step together, right? So y2 is going to be y1 plus y1 prime times the step. And y1, we said it's 1 plus 5 over n plus 5 times 1 plus 5 over n times 1 over n. Now, here's the trick. Don't try to expand this in any possible way. Factor out 1 plus 5 over n. And then what remains? From here, you get 1. And from here, you get plus 5 over n. So what does that give you? 1 plus 5 over n squared. And that's on your first step. So on your second step. So on your first step, you had this. On your second step, you have this. An easy guess is that yn will end up being 1 plus 1 plus 5 over n to the n. And now the question is, what is the limit of this? This is where you have to use a little bit of calculus. But let me just say that the limit is going to, no, it's not t. It's not t. You know what? Okay, let me remember my high school years when we used to do this kind of tricks. You know what you do here? Here's what you, yes, Christian, that's precisely right. That's what it is. Here's how you do it. You can write this as n over 1 over n over 5, right? And then you write this as n over 5 all raised to the 5th power. And now the idea is that this quantity tends to infinity. If it tends to infinity, this whole thing tends to e. And so this tends to e to the 5. There are other ways to find this, but you know, this is one standard way to do so. Okay. It's a really nice one. Okay, so I hope that this helps. Is there any other question? I mean, the problem on the homework is identical to that. Is instead of 5, you have some other number, I believe. Is there anything else I could help you with? Please try not to submit the homework at the very last moment. Especially if you're having any trouble, send me an email. I mean, I won't be awake at 11 o'clock or 11:30 checking my quiz. But no, I'm not going to go over the quiz right now because it's very similar to the problems that we solved on Wednesday. Exactly because the problems, I just want to have examples of everything on my recordings. So you can always go back and review the problem from, but what I just did is very similar to what you were supposed to do on the quiz. And as I promised, I'm going to also post the solution of the quiz. Actually, one of your solutions will be chosen and will be posted, the one that the grader deems as the best one. So why don't we get started with our first equation that we're going to solve for today. And these are the equations that show up like this. And this is where you're going to see a sort of amazing situation. So imagine that you can isolate the derivative in the differential equation, and you have something like f of y times g of x. Here, I'm supposing that y is a function of y of x. So in other words, you have isolated your variable, and the right side of the equation, the right-hand side of the equation, is actually a product of quantities in the respective variables. Okay, that is the assumption here. And if that is the case, here's what you do. And this is amazing because you know what, in Calc 1, when we were introducing the Leibniz notation. One of the first things that we said about the Leibniz notation was what? That, look, it does not it does not, it is not a quotient, right? That's what we said back then. That's the first thing that anybody says when talking about the Leibniz notation. This is not a quotient, right? But look what I'm going to do now. Look what I'm going to do now. So I'm going to rewrite it. Rewrite my right-hand side. And now I'm going to execute the following thing that is going to look so strange. So I'm treating it as a quotient. And that's the reason. Here's the real reason why the Leibniz notation was never abandoned. Right? Why not? Because it allows you to actually solve, for example, differential equations like this. And this is just an instance. It's not even the whole story. And what you do now is you integrate both sides. And what I want you to understand is, depending on how complicated the integrals that you find are, you may actually end up getting a very implicit looking solution for your differential equation. Okay. The other thing that I want you to pay attention to is that you're having to you have to execute two integrations. So you will have to put just one C on one side. Don't put C's on both sides. Okay. So why don't we do an example so that we clarify what is going on? And let me get started with the differential equation, for example, that I discussed a moment ago, which was what? It was y prime is equal to 5y, right? And let's say, for the sake of the argument, that we also want to solve the initial value problem. There are situations in which the solution of an equation can be expedited if you use the fact that you have an initial value problem. But please understand that I will specifically avoid to take advantage of anything like that in what I'm going to do. In particular, I'm going to actually solve this as if I'm looking for the general solution. That is, as if I'm ignoring the initial value problem. Okay? So, so what do I do? I write dy over dx. Please pay attention to the fact here that since we do not know what the independent variable is, you can choose whatever you like. I mean, if somebody gives you the problem that I just gave you, and you prefer to solve to suppose that the independent variable is t, so be it. Okay, so it's not a problem. So dy over dx is equal to 5y. Now, what you do here is you will do dy over y is equal to 5 dx. Please understand that the 5, you could put it in both places. Okay, I choose to put it on the right. Okay, and now I integrate. This is where you need to know your integration, and you get ln of absolute value of y, right, is equal to 5x plus c. And again, you may ask, why do we put everything, why do we put c on the right and not on the left? And it's not a big problem, but here's why I'm doing it. There is still a reason why I'm doing this. And the reason is that I wish to actually solve for y. Meaning, if I leave it like this, I could leave the solution like this. And I could just tell you, you know what, the solution that we're getting here is implicit. And too bad, so sad. I mean, we have to realize that in many cases, we're going to get implicit solutions from differential equations. However, we say, you know what? If you can make it explicit, then that's certainly preferable, because that's the way that people operate when they have functions. They're used to think of it as input-output, right? So you want a nice solution, a nice form that gives the output in terms of the input. So that's why in the case of differential equations, the process of actually solving for the specific dependent variable can be a tricky one. And I want you to pay attention here what we're going to do. So the first thing that I do, and I'm doing it because I want to do this in every detail right now, is we raise e to that power. So e to the 5x plus c, right? And this becomes absolute value of y is equal to e to the c times e to the 5x. Do we all agree so far? Okay, good. So now it gets a little tricky. So the first thing I want you to get used to is the fact that treat the constants as generic constants. So I'm going to say now that this is any number. Well, not exactly any number. It is any positive number. So this is a positive number. And I could use a new variable, but you shouldn't feel compelled to do that. You can still stick to c. So in other words, I'm thinking of e to the c as a new letter variable. And then I tell myself, why don't I use c again? I mean, I like c. I just need to keep track of it and just say now that since I replaced e to the c by c, that c is positive. C is positive. I just have to say that. Okay. Why c should be positive? Because it's the value of the exponential function at c, right? The exponential function takes only positive values, right? E to anything, e to any real number. If you raise e to any real number, you get something positive. So now I'm removing the absolute value and I say plus or minus c e to the 5x, right? So I can now suppose that this is also a positive or negative number, but not zero. And here comes now the culmination of all this. I say, yes, fine. This is not zero. So I can now say that y is equal to c e to the 5x, where, no, actually before I should have said c is greater than zero because I have the plus or minus. Now, I get rid of the plus or minus, and I say that y is equal to c times e to the 5x with c different from zero. And whenever something like this happens, it's always a sort of natural thing to ask oneself, okay, is it still true that c equals zero will give us a solution? So I'm going to ask, does c equals zero give a solution? And of course, you're going to see that that is the case. Now, you may ask, why? What happened to c? Why can it be equal to zero? I want you to understand that in the process of solving the equation, we divided by y. Don't forget that. Don't forget that we divided by y, right? So supposedly, in the process of solving the equation, the case that the function is equal to 0 had to be excluded. That does not mean that it's an impossibility that you could have had c is equal to 0. And that's why we test it separately. That's why we test it separately. Okay, and finally, we give our solution. And we say y is equal to c e to the 5x. And guess what? I'm just saying, I'm not imposing any condition on c. I'm not imposing any condition on c. And that's it. Okay, and remember I had an initial value problem. So for the initial value problem, I have to do y of 0 is equal to 1, which means that which means that 1 should be equal to c times e to the 5 times 0, right? So I substituted 0 and 1, and that gives me that c is 1. So the solution of the initial value problem is y of x is equal to e to the 5x, and that's it. And that's it. Let's pause, take a look at the whole process, and let's ask our questions.
Yes, can you explain how we got rid of the absolute value again?
Yeah, to get rid of the absolute value, we just acknowledged that if a number is equal, if the absolute value of a number is equal to a positive number, then the number itself is equal to plus or minus that positive number. Okay, so we put by putting plus or minus.
Okay, and then can you explain why c is not equal to 0 again?
C was not equal to 0 from the whole process. Remember, you have to realize how c was obtained. C was obtained initially as e to the c. Look at it. This can never be 0. And then we just put a plus or minus of a positive number. That cannot be 0 either. That's why we had to test c equals 0 separately.
Yeah, but why are you like highlighting that over there? Like, why did you say c cannot equal to 0? Is it because now it's plus or minus c?
Yeah, because initially it goes positive.
And
then I just made it plus or minus, which means if you have a positive number and you just put a plus or minus sign in front of it, what can you say about it? And the answer is you can say that it cannot be 0. That's all. Okay. If somebody gives you a positive number and you stick a plus or minus in front of it, what that means is simply that it cannot be 0. Any more questions, please? Okay, any more questions?
So what is the question should to ask me here? So what is the question should to say here? calculate what, compute what, so.
No, the initial problem here, I'm sorry I didn't write it, so let me write it here so that you can all see. Should have been solve the initial value problem and the process that we performed was the solution of this initial value problem. That's all.
Thank you.
Sure. Any more questions?
I guess just to confirm, like, why didn't we use Euler's method? Maybe I just missed it, or like, I guess I don't.
Euler's method is an
Or I guess
approximate.
Euler's method just tells us like a certain interval, right?
No, not at all. Euler's method is an approximation method. So
Okay.
you always use Euler's method in order to approximate the solution at a given point. With this method, not only don't you approximate, you actually find the solution, and not just at a given point, but everywhere.
Okay.
Okay?
Perfect. Thanks.
You're very welcome. So, and this is an excellent question. You will have the only time you will ever use Euler's method is when you are explicitly told to do so. Okay, so there will be instances like in the quiz, for example, where I ask you to use Euler's method. In every other case, you will actually try to solve the equation. Okay. So why don't we do one more example? So this time I'm going to give you just a general equation, so not an initial value problem. So solve x, y, y prime is equal to ln of x. Okay. Why don't we solve this? Okay, let me give you a couple of minutes to work on this. I'm so sorry. Let me rewrite it so as to make sure. No, it's not m. I can see how it can be. It's ln. Okay. One thing that I would like to clarify, some of you actually might be wondering this, is remember solving the equation at first and obtaining an implicit solution was the easiest thing in the world. I hope you agree with me. So I'm talking about ln of absolute value of y being equal to 5x plus c, right? And then we spend most of our energy trying to make that implicit solution explicit, right? So the question is, on homework problems and on exams, I mean, in real life, you always want to make the solution as explicit as possible. That goes without saying. Okay, but for quizzes and for our exams, should you try to actually do the same thing? Should you try to make your solution explicit? The answer is generically no. Meaning, if I give you a problem where I do want you to make that explicit, I will have to tell you that. Okay, so in other words, put all of your energy in obtaining a solution. Little by little, you're going to start discerning when that solution can be made explicit and when you will have to settle for an implicit solution. Okay? And let's solve this one together. So let's write it as xy times dy over dx is equal to ln of x. So separate the x on the one side, the y is on the other side. So y dy is equal to ln of x over x. I want you to understand that whenever you solve an equation using this method, you're making some concessions. Silently, you're making some concessions. Some of these concessions always already come with the form of the equation. So for example, you divide by x cannot be 0. Okay, the moment you do that, you limit the domain of definition of the solution that you may obtain. That's why when that happens, you may want to go back and see if the solution that you found can actually be extended to 0. So these are sort of tricky parts, and they usually have to do with specific applications that you're going to have. Or ln of x here, x has to be positive actually. So it's even more restrictive than saying that it's different from 0. It has to be positive. So these are things that you may have to go back and sort of redo them and ask yourselves if they are going to, if you can actually extend the solutions to a larger set. But in any case, here we're ready to, let me write the dx here, and now we're ready to integrate. So we will have y dy is equal to the integral of ln of x over x dx, and that will give you 1/2 y squared is equal to 1/2 ln of x squared plus c, and that's it. Okay, that's it. For those of you who may be wondering for the second integral, let me do it on the side. I promise you that I will try to do as much background material as it's possible. So here I'm going to use a substitution. U is equal to ln of x, du is 1 over x dx, and that will give you u du, which is 1/2 u squared plus c, which is 1/2 ln of x whole square plus c. Okay, and that's how we found this integral. Questions, please. Questions? So in some sense, this is the simplest method of solving a differential equation. I sometimes do this in a calculus course, just to show why the Leibniz notation, this is where you get convinced that the Leibniz notation has survived through the centuries, exactly because it helps us do things like that. Okay, would it have been possible to do them without the Leibniz notation? Sure, sure. But the Leibniz notation works perfectly. I mean, these things that we do are pretty mathematically pretty grotesque, right? To take dy over dx and separate the dx from the dy, that looks pretty bad. Okay, that is almost indefensible from a purist's point of view. But it works in practice. Okay, it works in practice and it tells you why Leibniz notation is not going to be dropped. Okay, I think it's fair to say that this is pretty much the one instance where the Leibniz notation is going to be most so important that this is not going to be the case in other situations. Are there any more questions, please? Okay, why don't we take a break for a few minutes, and like 5-6 minutes, and then we'll come back with linear equations. Okay, everyone, welcome back. Let me see if we have any questions on what we did in the first part. So it is now that the real fun begins. We're going to discuss linear equations. What's a linear equation? So a linear equation is, why don't I begin with an example? So something like this, y prime plus y is equal to x. This is your typical linear equation. So you do not have y squared, square root of y's, e to the y, or things like that. You do not have any of these things appearing. Other than that, you can have generic functions multiplying your y prime and your y. So you can have something like f of x times y prime plus g of x times y is equal to h of x, right? You can have something like that. And we will always want to pretty much leave y prime alone. So we will want to divide by f of x. And this will be called the standardized form. And in order to lighten up our notation, allow me to denote g of x over f of x by p of x, and h of x over f of x by q of x. So this will be called standardized. So what is in front of y prime is, so y prime has coefficient 1. Okay. So this is the equation that I would like to show you how to solve. Ready? Any questions before we do so? Okay, let's do it. So we want to solve this equation, and this is where the really nice ideas are going to come over. So expect the course to look like this in the long run. So we will be looking at specific types of equation, and we will be doing pretty interesting things in order to solve them. And what I'm going to do here is usually called, I mean, it has a general naming. There's some general terminology in mathematics. I'm going to multiply by an integrating factor. The idea is that I want to make the left-hand side the derivative of something, And this integrating factor, at first, it's going to look very strange, but I'm going to integrate multiply both sides by the e to the integral of p of x dx. And I could simply just tell you that I'm multiplying by e to an antiderivative of p of x. That would be a slightly better, is equal to q of x e to the integral of p of x dx. And now what happens is that, let me write it one so that you can see it. So we have y prime times e to the integral of p of x dx plus y times e to the integral of p of x dx times p of x equals q of x times integral of p of x dx. And this is why is this so important? Because if you pay attention, you will see that if you think of the function y as f, then you have f prime. And if you think of the function e to the integral of p of x as g, then you have f prime g. And this is f. And believe it or not, that's the upshot of all this process, that this is the derivative of g prime. I'm sorry, the whole thing is the derivative of g prime. So in other words, it's as if you have fg prime by the product rule, which means that what you have on the left is simply y times the integrating factor derivative equal to q of x times e to the integral of p of x dx. And of course, this means that y e to the integral of p of x dx is equal to the integral of what you have on the right-hand side. And that's the end of the story. At the end of the story, with some things to be noted here. So first of all, you will see this will be a common situation in many cases, that you will have certain integrals that will appear in the solution of a differential equation. Nobody can guarantee from the beginning that you will be able to compute these integrals. Okay, so here I have two integrals for you. First, I have this integral. And then I have this integral. So solving the equation is actually subject to being able to find those two integrals. And it is very possible that you cannot find those two integrals. This is very possible. Okay, so as long as we're able to compute these integrals, then this gives us the solution of the differential equation. The way it's given, it's implicit, but it can be made explicit simply by dividing by e to the derivative of p of x, e to the integral of p of x dx. So this is the theoretical description. Fortunately for us, fortunately for everyone, we will not have to, keep coming back to this expression, but we will just need to do it through specific examples. So let's do a specific example. Okay, so imagine that you have something like x squared y prime plus x y is equal to x cubed. Let's say we have this equation. Okay. There is a certain process that I want you to follow here. And when you look at such an equation, you have to ask yourselves whether it's separable. So it's not like you will be asked to solve equations under the assumption that they are of a specific type. You will have to figure it out yourselves. So for today, we have separable equations and linear equations. Always start by asking if an equation is separable. So for this equation, if I gave you this equation like this, of course, I'm giving it to you as an example of a linear equation. But this does not discount the fact that we have already explained separable equations. So it makes sense to ask ourselves if this equation can be separable. Okay, so what would you do in order to understand whether it's separable or not? The quantity that you have in front of y prime is just x squared. So it's a product of two quantities in x and y, x squared being a quantity in x, the function on being a quantity in y. So you should try to see if what you have on the, if you isolate the part that has the y prime, if what you get on the other side can be factorized as a quantity in x times a quantity in y. So what do you think? Can I factorize what I have here as a quantity in x times a quantity in y, what I have on the right? No. So not separable. Okay, so in general, the general wisdom here is that if it is separable, solve it as separable. If it is separable, solve it as separable. Okay, but this is not separable, so we move on. We solve it as linear. So step one is standardization. So step one is standardization. What do we mean by standardization? We divide so that the quantity in front of y prime is equal to 1. So we divide by x squared. So what do we get? Y prime plus 1 over x times y is equal to x. I divide it through by x squared. Is everybody with me so far? Okay. So now what you do is you focus on the factor in front of y. That's your p of x. And what do? You want to take the integral of that one. And this is where things become interesting, because what is the integral of 1 over x? Everybody will rush to tell me it's ln of absolute value of x plus c, right? I mean, you all know this integral very, very well. Yes, sure. But I will tell you that you can simplify it, because all we need is a specific integrating factor, a specific function, so that when we multiply the left-hand side by that function, it becomes the derivative of something that we can identify. Okay, so first simplification, you don't need the c. Okay, nobody told you to multiply by the most general thing that will make the left-hand side a derivative, easily a derivative. And secondly, I'm going to get rid of the absolute value. Okay, so all I'm going to keep from here is just, so I'm not going to say it's equal, but I'm saying I'm going to keep just the ln of x. And then remember what your integrating factor was. Remember what we wrote before. It goes e to the integral of pi of x dx. right? So here, my integrating factor is going to be e to the ln of x, which is very simple. This is x. Okay, so I multiply all sides by x, so I get x y prime plus y is equal to x, and I know x squared, sorry, and I know right away that what I have on the left is the derivative of the integrating factor times y. I know that with eyes closed is equal to x squared. And now this means that xy is equal to the integral of x squared dx, which gives me xy is equal to 1/3 x cubed plus c. And I can leave it like this. If you want to make it explicit, of course, you can do it. Y is equal to 1/3 x squared plus c over x, in case you want to make it explicit. Okay, there's nothing wrong with leaving it as an implicit solution of the differential equation. Okay? Questions?
Yeah, how did you move from the xy prime plus y is equal to x squared to the step beneath it?
I mean, look, I can do it if you like in a formal way, but I do want you to remember, if we go back to the general solution, that what you will be getting on the left, oops, sorry about this. Oh, what was it? What you will be getting on the left always is the derivative of y times the integrating factor. You can always justify it in any specific context. That is, here, what is x? Let me open a parenthesis here. What is xy prime plus y? Isn't the same thing as x times the derivative of y prime plus the derivative of x, which is 1 times y? So isn't that, according to the product rule, xy prime? Yes, it is. That's the justification of this. But I don't want you to have to go through that. Okay, I want you to know that whatever you found as your integrating factor, which is this x, this what you're going to get on the left upon multiplying by the integrating factor is always going to be the integrating factor times y and the whole thing derivative. Okay? There was another question. So let me try to address all the questions here. So there was another question. How were we able to remove the absolute values? It's not a result of a formal process removing the absolute values. It's just the fact that we need something very specific. We just need a specific function, and we can simplify it as much as it takes. If we left it with the absolute value, we would just make our life miserable, and it would still work theoretically, but you will see that in cases like this, you just simplify it easily this way. Okay. Any more questions, please?
Yeah, can you show how we moved on to the step after that? So for the xy that are in parentheses prime, so how would you write that? Like, I feel like there's stuff missing in between that and the step after that.
No, actually, there's nothing missing, but let me explain it to you so that I can convince you that nothing is missing. The point is this, that whenever we say that the derivative of a function is equal to g of x, so the derivative of f prime I'm sorry, the derivative of f, meaning f prime is g of x, that automatically means that f of x is the antiderivative of g of x. That's what is going on. Okay? Meaning any relation of differentiation gives you automatically a relation of integration. So if the derivative of what you have on the left is what you get on the right, then the integral of what you have on the right is what you have on the left.
Oh, okay.
Okay. You will see that the theory of differential equations. So first of all, it is natural for anybody who sees these things for the first time to look strange. Okay, so let's get this out right now, right away. Okay, so yes, they have to look strange in the beginning. The idea is to try to do these examples as many times as possible. Okay, and little by little, these notions that are direct consequences of the standard things that you learned in calculus are going to become much more natural. Okay, that's the one nice thing about differential equations, that you finally get to see how calculus works. Okay, so in calculus, you learn fact after fact after fact. And yes, there were a few cases, maybe my favorite is in the theory of Taylor series, where you get to use some of the things that you learn, but in some sense, you don't get to use them other than in immediate examples that are pretty much the same thing as the theory. Finally, when you do differential equations, you have to use what you learn as tools. Okay.
Okay, and then final question. What was the question for this question?
Find the general solution of this equation, right? So find, let's write it here. So find the general solution of. Okay, and that's more questions, please. Okay, let's try this. Y prime plus somebody has their, okay, let me mute everyone because somebody is, so y prime plus tangent x y is equal to 1, let's say. Okay, try to solve this equation. Okay, it's a linear equation. It's not separable, so don't try to treat it as a separable. And also, while you solve it, let's take our attendance. So give me the word linear on the chat. Okay, send it to everyone, please. Okay, try to solve this equation. that's a hard question. You know what? I'd rather address such a question. So one of you is asking me whether you can use other methods other than the ones that are presented in the lecture. The easiest thing is to say here is I would be very curious to see what you mean. So why don't you visit me during my office hours and tell me how else would you would like to solve these things, so that we can have a sort of educated discussion. Okay. The reason I'm saying this is because with most shortcuts, you might be getting some yeah, all sorts of strange things, but so this is already standardized, right? So so you need to find the no, that's too late, Yusok. Okay, so whenever I give you the keyword, it has to be within 30 seconds or so. Okay, so I understand that sometimes you can step away, but and then absence doesn't matter, but please try to give your attendance within a few seconds of when I say so. Yeah, and that goes to everybody. So like I said, for once it doesn't, or twice it doesn't matter. So this will be so let's find the integrating factor. So we will have e to the tangent x dx. Do we all remember how to find the integral of tangent x? Let's do it real quick. This is the same thing as sine over cosine. And here you do a substitution. U is equal to cosine x. So du will be negative sine x dx. So you will get minus du over u with u equals cosine x. So that will give you negative ln of absolute value of u plus c. And here you can do just minus, or so I should put an arrow so that we obtain minus ln of cosine x, which is ln of secant x, right? Because the negative sign can go inside the ln as an exponent, so it's ln of 1 over cosine x, and that gives you ln of secant x. So when you take e to the ln of secant x, that's secant x. So you can rewrite your equation as y times the integrating factor, which is secant x all derivative, is equal to 1. And you will get y secant x is equal to the integral of 1 dx, which means that y secant x is equal to x plus c. And that's, and again, you can easily make this explicit. Okay. So let's recap. We do not have class on Monday, right? Let me double check the calendar. I'm pretty sure about it. You can easily go there by checking the academic calendar. So for summer, it says July 19th, which is this Monday, is Juneteenth So there are no classes. Okay. So our next class on Wednesday, and that's why the second homework assignment is due on Wednesday. I also gave you a another I'm sorry. I also would like to remind you that your first homework assignment is due tonight. So please do that. And the quiz for Wednesday, yeah, there will always be a quiz when there was a class before. So the only time that we're not going to have a quiz is after the midterm exam. Okay, after the midterm exam, we're not going to have a quiz. Okay, so we're going to have a quiz, and I will give you one equation. It will be either separable or linear, a simple example. But I hope that our quizzes are going to get more interesting as we go. Okay.
So are you hosting office hours on Monday or?
No, I'm sorry. I will observe the holiday, so my next office hours will be on Wednesday at 11:50. Okay, but I'll be happy to answer any questions over email. So I wish you a nice long weekend. Please work on everything. If you need any help, any assistance, shoot me an email. And I will see you on next Wednesday. Okay. Take care of yourselves.
Have a great day.
You too. Thank you so much.